join or have for yourself. So that does it for me. Now I'll pass it over to Ms. Kendra Snow-McGregor.
Great, thank you, Clay. So before we begin, I want to talk a little bit about what we're going to discuss. We're going to be talking about fractionation, understanding your column from first principles. And in terms of hardcore process engineering, this is probably one of the most technical subjects that we can have. And really the approach that we're going to take is at very much so a high level. And I just want to recognize my co-authors on this, Mr. Bob Hubbard and my good friend Gerard Hageman. And so I just wanted to give my co-authors some recognition. So thank you guys for all your help and support on putting this topic together. A little bit about me. I have a bachelor's and master's degree from the Colorado School of Mines. I'm the discipline manager for oil and gas processing, and I'm a senior instructor and consultant for PetroSkills. I have over 23 years experience in the oil and gas industry. Prior to joining PetroSkills in 2008, I worked for 2 significant engineering, procurement, and construction companies. I've worked a number of different projects from major international oil and gas companies to very small shale MLPs. I published a number of different papers and I hold 2 technology patents. I've been very active in the industry over my career. Currently, I serve on the GPSA Board of Directors as well as being a member of the editorial review board that we manage the GPSA engineering data book. And so with that said, let's get right into the presentation. And so notice I'm showing a block flow diagram of our gas processing facility. And really what we're going to be focusing on is this block right here. So we're going to be talking about stabilization and fractionation. But before I go there, really what's important for us to understand is what are our liquid product specifications? Because I need to understand what I want my fractionation train to make. And once those products are defined, then their compositions are defined. And so what I want to talk about briefly is I want to talk about some common contaminants and the issues associated with them. But I also want you to come away with an understanding in terms of the factors that really drive my liquid product specifications. And so notice on this slide, I'm listing some contaminants. You can see the first one here is hydrogen sulfide. As many of you know, hydrogen sulfide is extremely toxic. But before I go to this slide specifically, let's talk about why do I need specifications in the first place. And really what's driving these specifications is safety in their transportation and safety in their end use. And so when I start looking at the contaminants and I start thinking about those, safety issues and what kind of problems might they cause in my, my product distribution systems or for my end users, and I think about H2S, I mean, certainly H2S is extremely toxic, but one of the biggest problems outside of that is that it's flammable. And when I burn H2S, I'm going to make sulfur dioxide and water. And so what you're looking at right there is our friend acid rain. All right. And so as far as an end user, if I'm going to be, using propane as a fuel, I don't want to have the off gas containing a lot of SO2. And so that's, one of the issues with our product specifications. You can see I have this other sulfur compounds down here as well. So any kind of sulfur compound that I might have in my stream will burn and cause me acid gas emissions, acid rain emissions, or SO2. The other problem with H2S and carbon dioxide, so I'm going to group these now into acid gas components, is that they are corrosive in water wet systems, okay? And so for my liquid commodities, I want to be sure that they're dry, so I'm going to have a specification on my total water, but I also want to be sure that I have adequate safeguards in terms of the maximum amount of H2S, sulfur compounds, and CO2. The other problem with CO2 is that it will decrease my heating value, and a lot of times where we will see that CO2 come into play is in our sales gas specification. Notice here's our friend water listed right here, and so water can cause me corrosion. I've discussed that previously. But if I get any small amounts of water in my, let's say my product propane, and I start flowing from my propane storage tank, if I have water in that system, I can start hydrating off on my level control valves or my dump valves coming from that tank if there's any free water available there. And so I have to be very careful with the amount of water. And then lastly, I do want to talk about my friend carbonyl sulfide. Again, COS can be difficult to remove in our processing schemes. And if I have any type of carbonyl sulfide in my propane system, unfortunately, that will react to form H2S in the presence of water. And if that happens in my product propane, then I can start going off spec on my copper strip test. And so I need to keep an eye out for COS as well. At any rate, just remember any sulfur species can cause corrosion, and all of those will contribute to my total sulfur content. And then lastly, I want to talk about methanol. And methanol is becoming a very hot topic nowadays. And really the biggest problem with methanol is that it's a refining and petrochemical catalyst poison. And so you may hear the term oxygenates. You can see in North America, we have a number of pipelines that have started instituting methanol specifications. And so this is something that's relatively new. And so you can see these pipeline specifications on methanol range from 0, no detectable oxygenates. Energy transfer pipelines are the same way, commercially free of all oxygenates, so that would be methanol. And then other pipelines to varying degrees will allow you to have some methanol present. And so that's one of the things that you need to be looking out for, because where we start really going off spec in terms of our methanol concentration is in our liquid commodity streams. You can see on this table here, this gives you an idea of some common product specifications, and these are given in terms of liquid volume percent. These example specifications come from the GPSA engineering data book. And so you can see I have a number of different liquid products that I can make. I could sell, maybe I want to sell ethane. And so in that case, I need a 95 volume percent ethane minimum with a maximum of 3% on the methane and so on. And so I can sell an ethane propane mix, different grades of propane, commercial butane, isobutane, normal butane, and so on. And so notice all of these specs in this example are compositional basis, and I also do have a vapor pressure spec. And so the reality is, if I know, what I want to make, and my buyers are going to tell me, hey, I'm willing to accept this product with this composition, and then when I go into my frac train, that's what those distillation columns must meet. Otherwise, I can't sell that product on the market. And so when I think about understanding my column performance, really I need to understand, what is my distillate? What am I trying to achieve in terms of my distillate composition? What does the bottoms composition look like? Which stream in that particular column is the most important? And then once I understand that, that's really going to frame what the requirements are in terms of that column performance and operation. I'm showing this slide here. This gives you an idea of different LPG type mix specifications. So again, I could have a commercial butane, and I can also have, maybe a propane HD5. So really, again, where all this comes from is, what are the contracts for your specific facility, and you can go and pull those and have a look. Then you'll understand, okay, this is the minimum that I must make, right? Because I can always, make a more pure product. My buyer isn't going to refuse that. But I do have some certain minimum specifications that I need to make. And so in terms of understanding how these columns actually operate, really understanding my qualitative phase behavior is the key. If I understand my phase behavior and I understand my compositions in that column, then I can understand exactly where that column needs to operate to be the most efficient operation. And so let's take a look now at multi-component phase behavior. Okay, so in this section, we're going to talk about my multi-component phase behavior. I'm going to explain why this phase behavior is critical in understanding my fractionation column operation. All right, so let's take a look first at my multi-component phase behavior. All right, and the first thing you guys need to walk away with is that the shape of this phase envelope is a function of composition only. All right, that's it. All right, so if I know my composition, I know my phase envelope. And if I know my phase envelope, I will understand exactly where my process is operating in terms of its qualitative phase behavior. And so let's take a look now at the information that we have on this figure. Notice here is increasing temperature, and here is increasing pressure. All right, and so you can see you have various regions. So let's say I'm a liquid and I'm somewhere out here. All right, out in this region, I am a liquid, and in fact, I'm way over here. So this would be a subcooled liquid. And let's say let's start heating up this liquid. All right, so I'm going to heat this up at constant temperature, and finally, at some point, I hit my bubble point, and that bubble point curve defines where I'm going to get the very first bubble of vapor. All right, and if I think about a multi-component hydrocarbon system, and I think about, you know, what I would typically have, I know I'm always going to have some amount of methane, I might have some ethane, etc., but it's going to be that light end that very first pops out of my liquid composition to create the first bubble. And so this bubble point curve is set by the light ends in the system. All right. The other thing that's important to recognize is when I'm at my bubble point, I am 100% liquid, but I am a saturated liquid. Another way to think of that is that liquid is at its vapor pressure. All right, so that's essentially the liquid's vapor pressure curve. Now, let's continue to heat this system. And notice once I go past the bubble point curve, I am now into the two-phase region. All right, and so if I know my composition, I know my temperature and pressure, I could plot that on my phase envelope and know exactly, you know, what kind of fluids I have inside the pipe. And so this is a very powerful tool in terms of looking into my, you know, process equipment. And so you can see at this point here, I'm now 25% liquid, so that's a quality line. And again, as we continue heating, we get less and less and less and less and less liquid until finally I hit my dew point curve. And so at this dew point curve, this condition here, I am now 100% vapor. All right, my entire composition is 100% vapor with the exception of the very last liquid droplet. And so that liquid droplet, if I start thinking about the composition in my multi-component phase behavior, that very last liquid droplet that's going to be hanging on to remain a liquid is going to be the heaviest hydrocarbon in that system. And so essentially the shape of this dew point curve here is set by the heaviest component inside of my mixture. Okay. All right, so that defines my bubble point, my two-phase region, my dew point. Now, if I continue moving out into this region here, let's say I'm all the way over here, I am now a superheated vapor, all right? And so that gives you an idea of what defines the bubble point and the dew point. And so let's erase all the ink on the slide. Now, let's follow the bubble point curve. And notice it terminates at the critical point here. And that critical point is simply defined where the dew point curve and that bubble point curve meet. A lot of times people say, oh, well, that's where your vapor and liquid properties become one. Well, they do. An easier way to think about it is, look, that's just where the bubble point curve meets the dew point curve to make the shape of the phase envelope. We don't want to operate in the critical point because it's a very unstable region. My physical properties can change very rapidly. So really that's about all you need to know about the critical point. Now notice as I follow my dew point curve along, I come up to this position called, excuse me a moment, I come up to this point here, and you can see at my highest pressure, I have my Cricondon bar. So my Cricondon bar simply represents the highest pressure at which I could have 2 phases for a given composition. And then if we continue on and follow that dew point curve down, you can see that I get to my Cricondon therm, and that's essentially the highest temperature at which I can have 2 phases. Okay, and so as far as understanding my phase envelope, it's important to understand the composition, obviously. Once I know that, that sets my phase envelope. And then notice I'm also showing this isothermal retrograde region. All right, and so let's take a look at what happens in that region. And what I want to do is start from point E. We'll take a look deeper in the phase envelope, but for talking purposes, let's start at point E. And so notice I'm going to go at constant temperature, and I'm going to take my composition, I'm going to start increasing the pressure. And so notice at some point, I get my very first droplet of liquid forming, I hit my dew point. Now I'm going to continue increasing that pressure. And when I think about a hydrocarbon system and I think about increasing the pressure on, what was a gas, I would expect my liquids, my heavy liquids, to start condensing out. And so that's what happens when I go from point E to point D. And so you can see what I'm looking at is the shape of these quality curves on the inside of the phase envelope. Now notice once I hit point D, these curves, the slope of these curves start changing. And so physically what happens is that as I go from point D to point B, I have now boiled off all of the liquid that I had condensed in here. Because you can see at point B, I am now back at my dew point location. If I continue heating that vapor up now, I will be a superheated vapor at point A. Now, here's the thing. Why do I care about my retrograde region? Essentially what's happening there is that's where life kind of goes backwards. So things don't happen the way I would expect them to happen. And so you can see if I move deeper into the phase envelope here, you can clearly see that by the shape of this quality line that I'm boiling off all the liquid that I condensed as I increase the pressure. So essentially what that tells you is that if and this is one of the reasons why we care, is if I have a gas that's at its dew point and I'm inside my process and I'm at point B, and let's say, I want to go into, I know this is a bit off topic, but I want you guys to appreciate why this is important to understand. If I'm going to go into my fuel gas system, and let's say I'm going to take a pressure cut to get into my gas turbine, and I'm at point B and I drop into my lower pressure system for my turbine, guess what? I dropped into the 2-phase region and I'm in the retrograde region. And so in the retrograde, I get increased liquid production at a pressure drop. And so now I have a big problem if I send that into my turbine, it'll destroy the turbine. And so that's why oftentimes what you will see is we will put in a superheater so that I can move my gas condition up to point A. So now when I take my pressure drop into my fuel gas system, I'm no longer going into the retrograde region. And so that's probably more than you needed to know in terms of phase behavior. But the reality is this is important. It's important for all facilities engineering. If I know my phase behavior, I can do a lot of troubleshooting just by simply applying my phase diagram and understanding where my process is operating. And so that's a key point. But back to the topic of fractionation. Now, remember, my compositions that I want to make out of these columns are fixed. So my dew point mixture. Clay, is there a question?
No
Okay.
questions. Go ahead.
All right, cool. Just checking. I thought I heard something. All right. So you can see here is my propane product. And so that's coming out of the top of my column. And so if I understand my composition, you can see this is nearly a pure component, very pure propane. And you can see here it's my bottoms composition. Those are the two streams that are leaving out of the top and the bottom of the column. Now, once those are fixed, that's essentially going to fix where my column is going to be operating depending upon what types of utilities I have in my system. And so before we go there, let's take a step back and talk about fractionation principles, and then we're going to start applying my phase behavior to this column operation. All right, so the first thing I want to talk about is stabilizers, because really a stabilizer is probably the most simple distillation column that we have. And so we're going to talk about how stabilizers work. Then we're going to describe how fractionators separate components into my two different products. And then we're going to be able to list the purpose for my condenser, reboiler, and reflux. And then we'll discuss what controls the column operating pressure and my required bottoms operating temperature. Could I ask whoever's not muted to please mute themselves, please? Thank you. All right, so moving on. When I think about stabilization, essentially what I'm doing here is I'm separating my hydrocarbons based upon their boiling point. And so this is a really simplified way to think about it. If I have a stabilizer, really all I'm trying to do is stabilize the liquid hydrocarbon so it can go into an atmospheric tank. All right, and so there's one product specification, and that would be my bottoms product. And typically this is a vapor pressure spec, or it might be a component ratio. And all I'm doing in the stabilizer is simply boiling the light ends out of that liquid stream. And so you can see this gives you an idea of the normal boiling points of some common compounds. And I want to pause a moment here because when I talk about fractionation, I will also talk about, well, you know, these columns are essentially separating the components based upon their boiling points. Another way to look at that, or something more, a tad bit more complex, is, you know, we'll talk about this idea of relative volatility. But really, when I look at the normal boiling point, let's say I want to separate my isopentane from my normal butane as a stabilizer, and notice I look at the differences in my boiling point. I go, you know, I have a really nice spread. That's a pretty easy separation. There's a big difference in my normal boiling points in terms of the products that I'm trying to separate. Once I go into, say, a depropanizer, let's take a look at what my light key and my heavy key would be. So if I have a depropanizer, I want to separate my propanes from my butanes. So this is my light key, and this is my heavy key. Right? And so I look at the differences in these two boiling points, and I look at that and I say, yeah, you know, that's a pretty easy separation. Let's say we wanted to separate our butanes, right? So notice if I wanted to sell isobutane and normal butane separately, remember these have the same molecular weights. I come over here, I look at their differences in the boiling points. You can see these are actually quite close. And so a butane splitter is one of the most difficult separations that we have. And so just remember, anytime you're looking at these systems, you can kind of think of them as separating the components based upon their boiling point. So back to my condensate stabilizer. Notice this gives you an idea of what it looks like. This is a very common layout. And you can see what I have here is I have my unstabilized condensate coming in, and notice I'm doing a split feed. So I'm taking my cold condensate or crude into the top of the column, and that's going to help knock down any heavy ends that might be trying to escape with the light ends that I'm boiling out. And so generally I take that stream back to the front end of my plant. You know, depending if I'm out in the field, maybe I'll use it for fuel. You know, it just depends. And then notice I take another portion of the stream, and I'm using my very hot bottoms product here. This is my RVP specification. I'm hot. I'm doing some heat integration. And so I'm heating up this feed here. I come, you know, down lower in the column, and then you can see here is my fire reboiler, and I'm, you know, maintaining this temperature in the bottom of the column here to meet my vapor specification here. And then the last thing that we see that we do is notice I'm going through this product cooler, because remember, this guy is going into a tank. All right, so I'm going to put this into an atmospheric tank. And what I'm doing here with this product cooler is I want to be sure There's my phase envelope. I'm trying to move that liquid away from its bubble point curve so I minimize any vapor losses coming off in that tank. And so that's another example of applying a phase envelope to understanding, well, why am I doing this in my process? So essentially, I want to store a subcooled liquid in my atmospheric storage tank to help minimize any vapor losses. All right. The other thing that you need to be aware of is that the top of this column is cold, the bottom is hot, and one of the things I care about is I want a very even temperature profile from the top to the bottom. And so by adding in the side reboiler, that helps me maintain a more steady or stable temperature profile. All right, so as far as an example fractionation train, notice oftentimes I will be taking someone else's Y grade. So you see I have my demethanizer here. I have my methane coming off. I may have a C2 plus Y grade. So in the States, we call this Y grade. And that could be C2 plus, or it could be C3 plus. And it all depends on how I operate this column. And then once I understand my composition here, and I know what products I want to make, then that sets how many types of fractionation columns I might need and how I need to operate them. All right, so let's take a look at how my fractionators work. All right, so essentially, again, we're going to be separating these based upon our boiling points, but the big difference now is I have a distillate and bottoms product specification. All right, before on the stabilizer, I only cared about the bottom. Now I care about both. And so what's happening is my reboiler is causing hot rising vapor to move up through the column. All right, so I'm boiling off the light ends in the bottom of the column. And so when I do that, two things happen. The hot rising vapor transfers some of its heat to the liquid, causing the heavier vapor components to condense back to the liquid phase. And the heat absorbed by the liquid causes the lighter liquid components to flash off and join the vapor flowing to the next higher tray. And remember, I have reflux coming at the top of the column, and so that's in the rectifying section. And so this is liquid that is cooler than the top of the column. It's flowing down. And so essentially, that's going to condense out any heavy hydrocarbons and cause them to flow down to the bottom of the column, and this is known as internal reflux. And so in a very simplified manner, I can think about my fractionator as a series of equilibrium separators. And so you can see on this diagram here, I have my feed coming in some point in the column, and then I'm putting heat in the bottom, my bottom's composition is coming out. I'm taking heat out the top, my distillate product is coming out the top. And remember, this is T cold, and this is T hot, and I want to try to have as smooth of a temperature profile as possible. Some other things to point out, notice my distillate product is the light key, and so for a depropanizer, that would be my propane, right, because I name my columns based on the distillate product. My heavy key here would be IC4, and so you can see there's my light key and heavy key. We call the top of this column the rectifying section, and we call the bottom of the column the stripping section. All right, and so let's now take a look at how does this physically work. And I'm going to do this from the context of the TXY diagram for a propane isobutane system. And this is at 250 psi. That's a very common operating pressure for a depropanizer. And so notice what I'm showing on this figure here is I have isobutane from 0 to 100% on the x-axis. And then conversely on the y-axis, I have propane from 0 to 100%, right? When I look at this region up here, this is my all vapor region. The region down below in blue, this is my all liquid region. And so this would be for any composition that I could have at any, notice here are my temperatures, all right? And so I'm defining the phase behavior for this binary system. When I go inside of that little envelope, that is my vapor and liquid region. And so if I understand that, I also know that this is my dew point, and conversely, the blue line is going to be my bubble point liquid. And so let's apply this TXY diagram to a separator. And what I want to do, I'm going to take a 50-50% mole isobutane propane mixture, and I'm going to put it into the separator, and we're going to separate it at 160 Fahrenheit. And so notice if I had this system and I started heating it up, at some point I'm going to get my first bubble of propane vapor, and then notice we continue heating it up. I'm going to go into the two-phase region until I finally boil off until the very last droplet of isobutane, and then I can continue heating the system, and now I'm in the superheated vapor. And so if I were to heat this, if I had the system at 160 Fahrenheit, notice my vapor composition here is roughly, all I have to do is go over my dew point line, draw a line straight up. I'm 58% propane. My liquid composition down over here now, coming out of the separator, is 56% isobutane. And so if I look at my depropanizer operation in terms of a series of flash separations, where I'm going to take heat out of the top of the separator above and put heat into the bottom of the separator, and I plot this on my TXY diagram, notice my bottom temperature condition here, I'm going to say that's 166 Fahrenheit. I'm going to put my top temperature at 156. And so notice by the time I come out of the top separator, I have 63% propane, 37% isobutane, and the liquid leaving the bottom separator, the hot separator, is 37% propane, 63% isobutane. And so essentially, what's happening inside these columns is I just keep adding the number of stages that I need until I get the product purity that I want. And so you can see in this example, I've added another additional stage. Now I'm all the way up to 70% propane purity on the top, and I'm almost 70% isobutane on the bottom. Okay, so that gives you an idea of physically what's happening inside these columns. And so when I think about a fractionator as a number of equilibrium separators in series, remember I'm going to go back to this diagram here. And so essentially what we just looked at was a fractionation column as a series of separators where the top separators are cooler. I'm sending that cool liquid back down and heating it back up, right? And then the bottom separators down here are warmer. And that's how I'm getting my two components to split. And so the first takeaway that I need you to remember is that the more stages I introduce into a column, the purer products I'm able to make. All right, so the taller column I have, I will be able to make a much higher purity product. All right, so that's the first point to remember. The second point is, what's physically happening inside of that vessel, those really tall, shiny columns. So notice when I look at this figure here, I only have one heater in the bottom, that's my reboiler, and I have one cooler, which is at the top. There's my condenser. And so remember that figure I was showing before, I had all these heaters and coolers in between each separator. And so the question is, well, where are the coolers and heaters? So let's take a look. And so this is going to be, this example we're looking at would be a fractionation column where I'm running in full recycle. And so this is essentially the best way to start up a column. You charge it, and then you just run it on full recycle until you get your product specs, and then you can start introducing feed. And so notice I have no distillate product coming out. I have no bottoms product coming out. And so let's take a look at what's happening at this separator right here. All right, so let's take a look at that tray or that flash vessel. And so notice what's happening in this flash vessel is I have a liquid stream that's pouring down from above, from the stage above. Remember that stage above is colder. And so this is cold liquid, and I need to heat it because I need to partially vaporize some of that liquid stream. And conversely, the vapor that's coming up from below, that's hot, right? And so I need to cool that vapor off, and that needs to be partially condensed. And so essentially what's happening is by intimately mixing these two streams, the heat duties cancel each other out, all right? That's a big deal. When I think about my mass and heat transfer in the column, that ability to be able to get the hot rising vapor to mix with the cold liquid that's flowing down the top of the column is critical in terms of getting that column performance to be able to meet that specification. And so that's the other point to remember. Essentially, a distillation column is nothing else than a series of flash vessels where the vapor and liquid feed streams are intimately mixed to enable mass and heat transfer, after which they are again separated into a vapor and liquid stream. Okay, so when I take it down to like the very, very fundamentals, my fractionation columns are actually quite simple operations. Let's take a look now at our phase behavior, because remember I said that was the key to understanding my column operations. And so notice I'm showing my phase behavior, and I'm saying, hey, this is my roadmap to the depropanizer operation. And I'm showing you my distillate product phase envelope. I'm also showing you the bottom product that's leaving that column. And so notice in this example here, I'm controlling the column pressure by condensing my distillate at 120 Fahrenheit. And so let's see what's happening in this column. So essentially, I control the column pressure by the condensing temperature of the distillate. And so if I condense at 120 Fahrenheit, notice my column pressure is 230 psia. All right? That's essentially the pressure in the column here. That is how I'm controlling my column pressure. And remember, I have to have this composition because that's what I need to make to be able to sell to my buyer, all right? And I can control that composition by the reflux. But essentially, that column is being controlled by the condensing temperature of my distillate product. Now, let's take a look at what happens on the bottoms product. My column pressure is set. That's fixed. And my bottoms product composition is fixed. Its phase envelope is fixed. And so as a result, that fixes my required bottoms temperature that I need at the bottom of the column to get the separation to make. And so when I take a step back and I say, look, you know, what's really happening inside these columns? How can I break this down to the most simple operation? I just need to understand my phase behavior, and then I can understand, well, exactly what is my temperature and pressure going to be for changing ambient conditions? Because notice this is an air-cooled condenser. And so when I think about my facilities, you know, daytime, nighttime, summer, winter, we know that we don't always have the same temperature coming out of our air coolers. And so, for example, let's say I could get my distillate condensed at 80 Fahrenheit. Notice this is a big deal. When I condense at 80 Fahrenheit, my column pressure now is 145 psia. That's a really good deal. All right, that's a good deal because notice what happened to my bottoms required temperature. It's now down to 205 Fahrenheit. And so one of the keys in understanding my fractionation column performance is understanding the effect of column pressure. And so the lower I can operate a column, the more efficient that separation is going to be. And so we'll talk a little bit more about that here momentarily. And so now what I want to talk about is really what are my control objectives and what are some options to possibly optimize these columns. And so the first thing I want to talk about is, you know, what are my column control points and what are my typical manipulated variables? Then we're going to talk about the 4 primary column operating objectives. And then we'll talk about some options to optimize my column performance and plant profitability. And so when I think about my column control, unfortunately, this is where life gets really complicated because I have multiple control points. So I know I need to control my bottoms composition, distillate composition. That tower pressure is critical, right? Because remember, I'm boiling liquids in this ginormous vessel. I need to control the level of my accumulator. Got to be worried about my feed surge drum and the level in the bottom of my tower. And then notice to control all those points, I have a number of knobs that I can turn. And so if I had a constant feed rate, there are 120 ways that I could combine my controlled and manipulated variables. And so what I'm going to look at here may not be, you know, similar to how you're running your column because we can set these up a myriad of ways. But the example I'm going to look at is shown here. And so notice what I'm showing is I'm controlling the column pressure by controlling the heat removal on my condenser. All right, so that essentially sets the column pressure, and we saw that from the phase envelope, so we understand how that works. And so you can see my tower pressure is being controlled by the heat removal at the condenser. And then notice my reflux rate here. I'm controlling the temperature, it's, maybe third tray down, by my reflux rate. And so that essentially controls my distillate composition. All right, so that controls my distillate composition. Notice my level in the accumulator is being controlled by my distillate offtake rate. So there's my level. And you can see that my bottoms composition here is controlled by the heat input in the reboiler, and the level in my tower is controlled by the bottoms rate. All right, so that's a pretty typical setup. In terms of my operating objectives, now that we took a quick look at the controls, really the first operating objective is safe and reliable operations. And so remember, I want to keep my facility in this area, right? So just safe and reliable operations, that's operating objective number one. As far as operating objective number two, really what I want to do is I want to make products that meet the required specification. And what I'm showing here is my impurity, increasing impurity in the product. And you can see here is the selling price of my spec product. And notice this curve right here is my operating cost. And so what I want to do is maximize the acceptable amount of impurity in my product, i.e., all right, another way to say it, do not over purify. All right, that's a big deal. I mean, you need to be sure that your products are meeting spec, but the more pure you make your product, the less profit that facility is going to make. All right, so you're cutting into your profit. All right, and notice if I make it very pure, now my operating costs are so great that I'm actually running the plant at a loss. All right, so do not over purify. That's objective number two. And so let's take a look now at how do I manage this. And so really what I care about is this reflux ratio, right? Because I know any amount of cold liquid that I send into the top is going to affect the reboiler at the bottom, because there's a certain temperature profile I need to keep. The more reflux I put in, the greater the reboiler duty, but the purer distillate product I'm going to make. And so you can see in this example here, for a reflux ratio of 2.7, I'm meeting my required distillate composition of 95% propane. This isobutane is acceptable, all right? The other thing that's interesting to note in this diagram is up in this part of the column, there is 0 C5, all right? We are all light ends at the top of this column. And then you can also notice what's happening to the temperature profile here. And so typically, if I'm going to be controlling my reflux off the temperature, it's going to be somewhere down in this part of the column. All right. All right. So that gives you an idea of reflux ratio equals, 2.7. And so notice my reboiler duties, call it 31 million BTUs an hour. Now, let's say I'm going to increase my reflux ratio now to 3.5. And so now this reflux ratio is essentially, the amount of liquid I'm sending back divided by my distillate product I'm taking off. At 3.5, I'm getting 97% propane. I can sell that. My buyer's happy. He'd be more than happy to take 97% over 95%, right? But notice what happened to my reboiler. Now, instead of burning 31 million BTUs an hour of fuel gas, I'm now burning 36 million BTUs an hour of fuel gas, or essentially a 10% increase in my reboiler duty, right? And so that all translates into fuel gas, that translates into operating cost. And then again, the thing to be aware of is that there is a minimum reflux ratio that I need. And so if I drop that down to 2, notice my propane quality tanks to 87%. I'm not meeting specification. If you look at your column temperature here, we're really hot. We're definitely not sending back enough reflux to meet what our column needs to do, but you can see the other thing that's happening is that reboiler duty also goes down. And so what you guys probably observed is that there is a relationship between reflux ratio and reboiler duty and percent IC4 in my distillate product. And so you can see as I start increasing my reflux ratio this way, my reboiler duty starts increasing and my impurities start decreasing. As I start decreasing my reflux ratio, my IC4 starts going through the roof and my reboiler duty starts tanking. And so remember, what I'm trying to do is find the sweet spot in terms of my column performance with that reflux ratio. So try to find what is that minimum. Now, the other thing we need to be aware of is that there's a cost associated with off-spec product. And so again, I'm showing this in context of the impurity in my feed. Here's my selling price of the product. And notice now I have to subtract off my rerun costs. And so that's going to eat into my profit. And so one of the things is you do not want to accidentally drop your reflux level down to where your distillate product now goes off, because you're going to have to take that product and rerun it, and that's going to cost you additional operating costs, i.e. lost profitability. So the third operating objective is to keep your operating costs at a minimum. And the way I can manage that is I need to have a minimum operating pressure. All right, minimum operating pressure means minimum relative volatility, i.e. easier separation of those components in the column. That translates into minimum reboiler duty. And so it's easier separation, so I don't need as much reboiler duty. In addition, I need a lower temperature at the bottom of that column because my pressure was reduced. And so that will minimize my operating costs. And then I want to optimize my reflux ratio to meet just that specification. And so this essentially minimizes the internal reflux that's happening inside that column. And so if I come back here and I look at, a bigger picture of, well, okay, how can I put all these pieces together? This gives you an idea of what PFD level pressure control with an air-cooled condenser would look like. And so notice I do have a hot gas bypass that goes around my condenser, especially if I'm, operating somewhere in cold climate. But essentially, I'm controlling the pressure here by the heat removal out of that condenser. I will need a line going to flare if I have any light ends that accidentally get in my propane, for example. And then you can see the temperature control on that reflux lower down in the column. And so if I look at, again, the summertime versus wintertime operation, you can see that my column pressure goes down as I can decrease my condensing temperature. So I can go from 200 psia down to 160 psia if I'm condensing at 85 Fahrenheit rather than 100. But then also you see the benefit in the reboiler down here, where now I only need to meet a 211 Fahrenheit bottoms temperature here to meet my same product composition. And so one of the things that's important to recognize is, that internal reflux I was talking about. And I really like this diagram because I don't think people fully appreciate how much vapor liquid traffic we actually have going on in these columns to be able to get those liquids to separate. And so notice here is my feed coming in. I have 100 moles coming in. I have roughly 42 moles of distillate leaving, roughly 58 moles of bottoms product leaving. All right, and notice my reflux ratio, the sweet spot for this depropanizer was 2.7. As a result, the amount of reflux I'm sending back is 12% higher than the feed coming in. But notice what's happening to the vapor rate in here. The vapor leaving the top of the column here is 1.5 times the amount of the feed coming in. The liquids going down the bottom of the column here are roughly 1.7 times the amount of feed coming in. And so I need that much vapor liquid mixing and heat transfer in order to meet my product specifications. And so I'm showing on this table here some typical column parameters. And you can see here's my depropanizer typical reflex ratios, because remember there's an optimum there because it's a trade-off between operating costs and capital costs. But you can see I should be somewhere between 1.8 to 3.5. Notice here's that butane splitter. And if you think about that butane splitter, notice that reflex ratio could be anywhere from 6 to 14. So the amount of vapor-liquid traffic in those columns is incredible. And just always keep in mind that you have this relationship here, okay? All right, so the third operating objective is I really need to be sure that I'm maximizing my production and profitability. And so how do I do that? Well, first thing, I need stable feed flow rates, all right? I need to keep that column very stable. They do not like changing, swinging feed flow rates. I will not be able to maintain a product specification. Constant feed compositions are desirable. Changing feed compositions can cause havoc in these distillation columns and causing my compositions to go off spec. Stable column pressure. Remember, that's critical because everything, all the liquid in that column, I just have boiling liquid of different compositions from the top to the bottom. And so any pressure bumps can really cause havoc in terms of that pressure profile and what's happening with the mass transfer. Remember, minimizing that reflux flow rate, just use what you need. Minimum reboiler temperature, and that should actually say duty. All right, that's what I really want to minimize is the duty. And I want to maximize my higher value commodity streams. And so let's take a look at an example here. Notice, again, this is my depropanizer. And what I'm going to do is I want to maximize my higher value commodity. And so in this example, what I'm looking at is this isobutane, because I can sell isobutane for a lot more than I can sell my propane. All right, and so you can see in this example, if I run my reflex ratio to be 3, so my propane's a little bit purer, I'm minimizing the amount of isobutane going out the top, you can see I get 168 additional barrels per day of IC4 in my product stream. And you can see here's the commodity values. My propane price is roughly 38 cents a gallon. My butane price is 62 cents a gallon. And so the additional revenue that I can make over the course of a year would be $610,000 simply by running a higher reflux ratio to maximize my higher value commodity. There is a cost associated with that because remember, I have to pay for this higher reboiler duty here. Previously, it was, roughly 31 million BTUs an hour. So I have to pay for my higher reboiler duty. So you can see that's going to cost me $43,000 per year, but the other benefit is that I get an additional 17 barrels per day of normal butane, which we didn't include in the analysis here. And so with that said, that was all I was going to talk about in terms of fractionation. I know super fast paced. I just wanted to be sure that I respected everyone's time, but we do have time for our quiz and we will have Q&A at the end. And so before we go to the questions and answers, let's take our quiz and see how we did. So we're going to play Kahoot, and so what you're going to see on my screen looks like this, all right? And then I'm going to log in and I'll show a pin. This is not the pin, you'll get a new pin. And so what you need to do is use your phone and go to www.kahoot.it, or you could use the app, okay? And then what you're going to see is your phone here. And then when we're playing, you're going to answer on your phone, all right? Don't try to click on the screen, all right? So answer on your phone. All right, so with that said, let me get the Kahoot going. All right, I'm going to start in 1 more minute. All righty, I think we're ready to go. All right, my hydrocarbon liquid product specifications are driven by safety in transportation and usage, all right? And so that's what drives those specifications. Carlos is in the lead. All right, nice work. In a fractionation column, my components are separated primarily based upon the differences in my boiling points. And Carlos is still in the lead. All right, excellent job. The greater the difference in my boiling temperatures, the easier the separation. And Brutus, now took the lead over Carlos. Nice work, but boy, you guys are neck and neck. All right, excellent job. The more stages, trays, or column height, the pure products that column can produce. Excellent job. Carlos is back in the lead, followed by Umberto. All right, beautiful job. Intimate mixing of the vapor and liquid streams on each tray is critical for adequate mass and heat transfer in the column. And Umberto now took the lead, followed by NS. All right, excellent job. The bottom product from a fractionation tower is always a liquid at its bubble point. All right, it's at its vapor pressure. And that's how we can use our phase diagrams to understand exactly what is that bottom's temperature required based on my column operating pressure. All right, Umberto is maintaining his lead, only 3-point spread with NS. Nice work. All right, good job. Distillation column pressure is achieved by manipulating the condensing temperature of the distillate product. And NS is now in the lead, followed by Carlos. All right, nice work. The first operating objective for a fractionation facility is make specification products. Do not over-purify. You're leaving money on the table if you are. All right, NS is in the lead, followed by Carlos. Next question. All right, second operating objective of a fractionation facility is to minimize your operating costs. And remember, we do that by trying to run our columns at the lowest pressure possible. And S is in the lead. Last question. All right, beautiful. The third operating objective of a fractionation train is to maximize the plant's profitability and its production. All right, Julian came in third. Carlos came in second. And NS was the grand winner. Nice job. Congratulations. Leave. All right, so with that said, before we take some questions, I want to thank everyone for attending. And so just real briefly, we have a number of instructor-led and virtual courses that cover this topic, primarily G4 if you want to get into the hardcore engineering bit. We also do specialize in operator training. And you can also see here we have a number of online modules that we have that would also be an option. And in addition, I know this is super high level. If you have any questions from today's webinar that don't get addressed in this question and answer session, feel free to reach out to me directly, and feel free to contact Clay if you have additional information that you want about our courses. And so with that said, Clay, I feel like we might have some time available to do a couple of questions.
Sure, yeah. Thanks, Kendra, for the presentation. I do have some questions here that came in throughout, so we'll go ahead and get to those.
Okay.
So from the beginning of the presentation, where you were showing the various specs, the question is, are the GPSA specifications common standard throughout the world or only in America?
You know, they're pretty standard. And the thing about it is, I mean, how would you know? You look at your facility's specifications. And then the other thing that you need to be aware of is that oftentimes, and I think this probably happens more, you know, with the gas stream, but if I have a industrial user that's somewhere nearby the plant, they might have a specific different need that is outside of these typical specifications. So certainly you can end up with contracts that don't look anything like this. And I guess the other thing I would say is it depends on, you know, also the pipeline. And so, for example, I was showing that demethanizer in the fractionation train, because really it's the first step. I need to make my Y grade to be able to make my final commodity products. And so I will have Y grade specifications or pipeline specifications that I need to make. And so this is an example here where that would be that mixed stream. And so these, you know, if it's a pipeline spec for moving an intermediate composition, those can range quite wild, have a wide range. And then the person who's setting that is the pipeline operator, because it's going to be set based on, you know, what's their equipment look like, what kind of, you know, vapor pressures, compositions can they manage. Good question.
Okay. Next question here has two parts to it. It says, I have a binary mixture. I want to get 99% purity of lighter component. How can I establish pressure and temperature to define in simulation software for sizing of column?
Right. So here's the thing. When we start looking at doing detailed calculations of these columns, and I didn't go into how do I set up my mass and heat balance, but essentially what we need to do, and this is covered in our G4 course, is I need to set up my shortcut calculations where I can do these by hand, or you can set them up. There should be a shortcut button in either Unisim or HYSYS. And so it does a shortcut calculation because that will tell you what range of pressures and temperatures you need to be at in order to get those two components to split. And so that's kind of outside the scope of this presentation. But when we do the written responses, I can send some references.
Okay, and then the second part is, for that same scenario, should I go for a packed column or tray column, and what should be the basis for that decision?
Oh, sure. So I didn't talk about the column internals just because of in light of time, but certainly I can use a packed column or I can use a tray column. And really what I'm looking at there is the amount of vapor and liquid traffic that I have. And so if I have a lot of liquid that I need to handle, let's say, you know, like in a stabilizer type application. Trays, multi-pass trays, give me the better ability to handle a lot of liquid and be able to get my good, vapor liquid mass transfer. When I think about packing, really where they work quite well is, especially a structured packing, is if I have very low liquid rates. And so if I have a situation where I have really low liquid rates, then I might be looking at a structured packing or maybe a bubble cap tray.
All right. Next question here also has two components to it. So the first part says, could you please shed some light on the phase behavior in the presence of moisture or free water in the stream?
Okay, so as far as my phase behavior and free water, and so I'm going to go to this diagram here. Here's the thing. I don't really have a lot of mutual solubility with water. And anytime I'm looking at my phase behavior for a hydrocarbon, I'm always looking at that on a dry basis. I can then go to my water hydrocarbon phase behavior and plot that water dew point, if you will, for a given temperature and pressure at which that hydrocarbon mixture was saturated. But in terms of the column performance, it doesn't affect the phase behavior for the bubble point and the dew point, but what it will affect, and I don't have a diagram in here, let me erase all the ink on the slide, what can happen where I can have problems with water in these systems is I can start, let's say I have a little bit of free water in my condensate coming into this column here. What can happen is that the bottom is too hot, and so now I have steam coming up, and the top up here is too cold for that water to leave as a vapor, and so it's condensing. And so what can happen, I can get a buildup of liquid water somewhere inside the column, and then it just slowly builds up over time, and if I don't have a water draw-off tray to be able to take that water out, I'm going to have pretty significant operating problems because at some point it's going to build up to be so great in that column that it just pukes up out the top, and then the column lines out, and then the process starts all over again. And so really understanding if I have a situation like that, certainly I need to know where that water is going to appear because I need to build those water draw-off trays before the column. It needs to be part of that column design. Once the column is built, that's a very difficult modification to make in the field.
Okay, and then the next part of that question is also, could you describe the effect of intermittent or continuous internal reflux on the smoothness of column temperature profile? And this is related to condensate stabilizer as it is defined by the efficiency of interstage/final cooler of overhead compressor.
All right, I kind of got lost on the bit of the overhead compressor part. Can you read that again, Clay, please?
Yeah, so the initial question was, could you describe the effect of intermittent or continuous internal reflux on the smoothness of column temperature profile?
Okay, so let's go to this slide here. Essentially, my internal reflux and the column temperature profile, those are married one-on-one, all right? And so if I do not have a good, smooth internal reflux here, let's say, and because remember, this is the vapor and liquid traffic that's going on inside the column. And so really what can happen is, if I had a side reboiler here that kind of went out of control and I vaporized all of the liquid off a tray, I have a big problem with my column operation. And so the actual temperature profile of being very even from the cold top to the cold bottom or to the hot bottom, I want a very even, steady profile. That's very important in terms of a steady internal reflux for these streams in here, because remember, that's what's driving the mass and heat transfer inside the actual column itself. the engine that's driving the bus is really the reboiler down here. But then remember, I need to send down the cold reflux to get my distillate composition to meet. But then once I have that set up, then it's all of this internal flow in here that's really driving that nice smooth temperature profile. And you know, the columns that I have shown in this presentation are really quite simple, where I don't have you know, side draw-offs with multiple side reboilers, etc. So things can get complicated, but yeah, if I lose control of the side reboiler, I get a hot spot or I get a cold spot, I know I'm going to have problems in terms of my column performance, because really the intent was to get good vapor liquid mixing on each tray.
All right, and then this is the last question, unless any others come in while it's being asked or answered. So this says, in which system can we use hot vapor bypass pressure control system to control column top pressure?
So here's the thing. I don't really use that hot bypass to control the column top temperature. I do need it to prevent. I need to be able to keep my my equipment stabilized in terms of not pulling a vacuum on that condenser. So where's this here? And so the other thing that can happen, so see, I want to be able to equalize these streams between the two. And then I know I'm showing this pressure controller here, but what can happen in really cold climates, let's say this air cooler gets out of control, or you know, I get a real cold winter night, and this pressure starts going down too low, then I need to have the ability to warm up and put a little pressure on this reflux accumulator. Otherwise, this column pressure is going to go too low. And there's always some, like, generally there's going to be a limiting piece of equipment in terms of what's the lowest I can operate my column pressure before something doesn't work. Oftentimes, it's going to be the net positive suction head required of those pumps. Or it could be, you know, that pump can't get into your product storage tank, if you will. So there's always some minimum that the system must have in order for all the fluids to be able to move around accordingly.
All right, that does it for the questions. Kendra, thank you so much for a great presentation and a great Q&A.
Oh, great. Well, thank you so much. And again, if there's any additional questions, don't hesitate to reach out. So everyone have a fabulous day, and thank you for joining.
Yep, thanks everyone. We'll get you a copy of the presentation afterwards, and we hope to see you in future sessions. So take care and stay safe.
All right. Bye, everyone.
Bye, everyone.